When I teach data analysis, as opposed to probability and statistics, usually we spend a fair amount of time describing how we can visualize the data. In this course, this isn't something we're really going to do, but I do want to emphasize the importance of visual summaries, as well as numerical summaries, which is what we've seen in a previous video. An easy way to visualize the distribution of one numerical variable is to use a box plot. It gives us a nice graphical summary of this univariate distribution, and only one variable at a time. This doesn't work for joint distributions. What you're going to do is you're going to draw a box along the observation axis. So if you have measurements, say, which are meant to be x values on the line, the box plot will be drawn along this axis. And your box is going to have two endpoints. The value for the upper endpoint will be the third quartile. The value for the lower endpoint will be the first quartile, and you're going to provide a belt, if you want, at the median. Now that's the box part of the box plot. These plots are also called box and whiskers plot because very often what you will see, I'm going to move now to the plot below. Very often what you will see are these little whiskers. And these whiskers are special lines. You will extend the line from Q1 here to the smallest value, which is less than 1.5 times the interquartile range to the left of Q1. And you will do the same thing for the largest value, which is less than 1.5 times the interquartile range to the right of Q3. There might be other values in your data set that are greater, further away than 1.5 times the interquartile range from any of the endpoints. Those you would plot separately as stars or literal dots. When points or observations are beyond the whiskers, which is to say, if you have a point which is more than 1.5 times the interquartile range away from the two endpoints of the box, then these are suspected outliers. Place them separately. They are not linked to the box with a line. Here are two examples of box plots. Now you'll notice one thing about the box plots is you can't tell how many points or how many observations you have in the data set. Now, you know you have at least two of them, right? I mean, there's a point right here. There's a point right here. These are observations in the data set that are within 1.5 times the interquartile range from any of the endpoints, Q3, Q1. So we know there's at least 2 points. There's going to be more than 2 points, otherwise we wouldn't have the structure we have here, obviously. And the median would be right in the middle, but only 2 points for sure. And here we know there's at least 3 points for sure. We can say a little bit more, like there's more than 2 points and 3 points. One of the things we could say is that it looks as though the second distribution has a suspected outlier. The first one does not. Even though a fair amount of the points are scrunched up here, right? This basically represents the 25% of the points within quartile 1 and the median. So 25% of the points that are close to the median very bunched up together compared to the 25% of the points here which are on the other side of the median between Q1 and Q3. So it looks as though the distribution isn't quite symmetric. Something you can measure with the help of a quantity called skewness. Skewness plays a role very much like that of the mean and of the variance or the standard deviation. It's an important quantity for distributions. In this course, we're not going to use it too much, other than to help us determine if the distribution is likely to be symmetric or not. If it is symmetric, the population median and the population mean are going to be equal, and the first and third quartiles should be equidistant from the median. If, on the other hand, you look at the distance between the third quartile and the second quartile, median. And that is greater than the difference or the distance between the second quartile, the median, and the first quartile, then you would say that the distribution is skewed to the right, right? The distance between the second and the third, here's Q2, here's Q3, here's Q1. The distance here is larger than the distance here. It is skewed to the right. In other words, you're going to have a distribution, it's going to have a tail to the right, or a longer tail to the right, possibly. The other way around, if the distance here is smaller than the distance between Q1 and Q2, we say that it's skewed to the left. In both of the examples in the previous slide, these ones, we had distributions that were skewed to the right. There's a longer bit to the right. Of course, here you have to sort of flip your point of view so that it follows the axis. Longer to the right than it is to the left, and similarly here. Now, I went all the way to the whiskers because there's still a fair amount of information here, but the test that we've gotten only talks about this distance being larger than this distance. That's how you determine skewness according to this test. Now, graphically, this is what you might see for the probability density functions. When there's no skew, the mean, the median, the mode, they're all the same. An example of that is the normal distribution curve. When they are skewed to the right, positively skewed, you should have a longer tail going to the right, which means that some of the highest values will pull the mean to the right. And in general, the mean will be greater than the median, which will be greater than the mode. So this is skewed to the right, or positively skewed. And conversely, if it's skewed to the left, you have a tail that is very long in the negative direction or in the left direction, which means that the mean is being pulled that way. A lot of the results that we are going to see assume that the distribution is symmetrical, that there's no skew. In practice, that might not be the case, but if the skew is slight, you might get away with assuming no skew. There's another thing you might want to look at in terms of dispersion measures. The standard deviation is one such thing, but I haven't really told you how to compute the standard deviation for a sample. You know how to compute the standard deviation if you have a PDF f at x, right? You're going to be looking at x minus mu, the mean, squared times the probability density function, and you take the square root of that. That's your standard deviation for the random variable. But that assumes you have a probability density function. If you're just working with a sample, you don't necessarily know what the PDF is. So you need to find a way to estimate this quantity. There's many ways to measure dispersion. The first one is the idea of the sample range. The range of a sample is simply to take the largest value that you have observed, the maximum, and you subtract from that the minimum value. Now, if you've ordered your observations, so x1 all the way up to xn have been relabeled, reordered y1 all the way up to yn, then it's simply yn minus y1. The interquartile range we've already talked about. It measures the distance between the third quartile and the first quartile. And the sample standard deviation S and the sample variance, these are estimates of the true underlying distribution sigma and sigma squared. Sigma squared being the variance, sigma being the square root of the variance. So if you have n observations, you can actually compute the sample variance, and this is important, using this formula right here. Very important. You start by computing the square of the differences between each observation and the mean observation, the mean value of the observation. This is important here Usually this would be a mu in your formula, but here specifically, you have estimated the mu, replacing it by the average value, the mean value of your sample. And then once you've done this sum, you will do an average of this sum, but it isn't the exact average. If this was the exact average, look here, you have n different values, you would be dividing by n. But that's not what you do. You divide by n minus 1. And you divide by n minus 1 because if you only divide by n, you will have a biased estimate. And we'll go right here, talk about this later, is that the expectation of this s squared is going to be the true variance. If instead you had used 1 over n, this wouldn't be true anymore. The reason why you have to subtract 1, and this is something we're going to revisit when we talk about linear regression, it's because you've already used your data to estimate one quantity, the mean. Like you've had to estimate it. So your data's already been used to some extent. And you can't reuse it again without losing some information. So we subtract the 1 here because we have lost 1 degree of freedom. We used the data to estimate one of the quantities that is required to estimate this other quantity. And if you're going to be using data to do double duty, there's going to be some sort of recognition, a penalty if you want. So this here, 1 is the degrees of freedom, which we've used to compute the mean, to compute the sample's variance. There's a more complicated formula, but nothing much is happening here. All I've really done is replace the mean of x by its actual value, and then work out the terms. And you will see if you do the full expansion, this is the expression you will get. Histograms are just another way to visually summarize the univariate distribution that we're given from a sample. This is the information that they should contain. They'll give you something about the range, the maximum value, and the minimum value. Once you know what the range is, you can start thinking about the number of bins you will want for your histogram. A histogram basically is a bar chart where the height of the bar tells you how many observations were found in each of the bins. Now that number of bins should roughly be the square root of n. N is your sample size, and the bin width in that case would just be r divided by k. You'll have to play around a little bit, obviously. If square root of n is not an integer, then you'll have to find the nearest integer. You'll figure out what's a good way to do this. The frequency of observations in each bin, as I said, is added to the chart. It's part of the height. Once you have this kind of information, you can start thinking about the shapes of data sets. So the box plots give you a very easy graphical means to get an impression for the shape of the data set. And we want to know the shape because that might help us decide what kind of mathematical model we need to consider to answer the problems of interest. For the box plot and the probability density function, so that the data is right skewed or skewed to the right if the box plot is stretched to the right, or if the probability density function is stretched to the right, you can make a similar observation about histograms. Here is an example of such a histogram. I have, well, how many bins do I have? I have 1, 2, 3, 4, 5, 6, 7 bins. I know what the range is. It goes between 35 and 0. And I can sort of basically guess the number of observations here. I have 10 observations, 14, 6, so that's 30 observations, 33, 39, 40 observations in total. This is the histogram of the number of accidents per day in Sydney, the data set we've seen before. So 40 observations. We decide to plot it with 7 bins, and we see that there seems to be a preponderance of collisions or number of accidents which are, below 15 daily, and not as many where you have more than 15 daily. The histogram is stretched to the right, like it has a tail. If you were to draw the curve that goes along with it, you'd probably draw something that looks like this. Stretched to the right, this is not symmetrical, just as the corresponding box plot is not symmetrical. and stretch to the right. Assuming that this is your axis here. Here's an example. I have a number of grades for a combined first assignment and midterm. So these are all grades out of 100. What can we say about this data? When you view it like this, it's a little bit hard to make any sense of it. There's numbers all over the place. I'm seeing 100 here, so somebody's doing very well. I'm seeing a 36 here, so somebody's not doing so well. What's the average? Would I even be able to say? What's the shape of this data set? What does it look like? If you want to follow along in R, you can just copy this bit of text here, and that's going to load the data set, and then you can run the other functions. We'll build a histogram itself, and then I'm going to use a function, the function mode, which will find me what the most frequent number is. Eventually, I'll put that into a nice plot and create a box plot as well next to it. Now, I can do some other stuff. I don't have to go for the visual display right away. I can do a summary of the grades, right? I can just literally ask what's the minimum, what's the first quartile, the median, the third quartile, the maximum mean value, and here you have it. So the grades range from 21 to 100. 75% of the grades are 55 and up. 75% of the grades are 82 and down, and 50% of the grades are below 70. 50% of the grades are above 70. This is what we get from there. You can compute other things as well using different functions. The standard deviation can be obtained, the skew, the kurtosis, things like that. We have a skew which is a negative value here. We'll see what that might mean in a second. Kurtosis we haven't talked about, we will not talk about, but it's a negative value as well. This is what we get, the distribution. This is the box plot of the distribution, and you can see that the grades are skewed to the left. The tail of the distribution is bigger or longer going this way, meaning that there's more observations congregating up here. It sort of makes sense, right? Because you cannot get grades above 100. So you would expect that if the mean is 70, there should be, or the median is 70, there should be more room this way. But it doesn't have to be this way, right? This is just an accident of the actual data that we've observed here. So this is a skewed distribution. What else can we say about it? Well, not much. I mean, the mean value is 70. There's a fair number of students here who had grades of 60 and up. If this was the grade distribution in my class, I'd be happy with this. It means that a fair number of the students would be doing fairly well. I mean, it wouldn't be great for some of the, not outliers, but the people who are further to one side of the distribution. But overall, I'd be satisfied with this grade distribution.